Section 2.2, 2.3, 2.4, maybe 2.5, I can't remember where it stops with all of our derivative rules, I think they're very fun sections. For those of you who like puzzles, I feel like they're kind of like a puzzle. So think, Sudoku, stuff like that. There's some basic rules. You follow the basic rules. You apply them in certain contexts. Sometimes you have to do a little bit of rewriting or figuring something out to be able to use rules. But that's what hopefully this will feel like in the rest of Chapter 2. 2.2 is our basic differentiation rules. They're the simple rules that we have, and there's a list of them. So we'll start with the constant rule. And I'll justify a few of them as we go because some of them are really easy to see why they are what they are. The constant rule is the equation f of x or y equals a constant. And if you think about what that line looks like, it looks like this right here. It's a horizontal line. And what's the slope of a horizontal line? 0. So the derivative of any constant is 0. Derivative of 5, 0. The derivative of 4/5, 0. The derivative of negative 4,372, 0. Okay, any number all by itself, the derivative is 0. The derivative of pi, 0. Okay, even numbers that we feel like are represented by other, Greek letters and things like that. Derivative of e, 0. Right? The power rule tends to be the one that people remember the most. I don't know if he could still do this, but my husband took calculus when we were in college, and it was the one thing that about 10 years later from calculus that he could remember. Like, that was it. His major did not include much calculus beyond calculus 1. So this is the one thing that he could remember from calculus. Those of you who have seen power rules before, do you remember what the derivative of the power x to the n is?
N minus 4.
Yeah, y'all are saying it right. So you bring the n exponent down, you rewrite the base x, and you decrease the exponent by 1. I don't know what. That's the one that likes to stick in our mind. N x to the n minus 1. Constant multipliers tell you that if you have a constant in front of a function, that constant just gets sort of dragged along as you go. So you take the c that's rewritten there, and then you take the derivative of the other piece like that. For example, if you had 4x to the 5th, the 4 would just come along and you'd take the derivative of x to the 5th using the previous rule. Okay? So the 4 as the constant just comes along. Now that's different than the constant rule at the beginning because that constant is not attached to any variables, right? Standalone all by itself. What's happening on number 3 is that it's attached to some other function that uses an x inside of it. Sum and difference rules. The sum and difference rules tell you that if you're adding or subtracting functions that you need to take the derivative of, much like with limits, we can simply take the derivative of each piece and then add or subtract those pieces together, whatever it was to start with. So it's sort of like what you would want to be true, kind of like with limits. We're going to find that doesn't happen always with derivatives, but it does for sums and differences. And then our last two, I'm going to throw one more in a minute here, but the last two that are specifically identified in your book are sin x and cosine x. And they have this very cyclic nature. So the derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. And it starts to feel kind of like back in the day when you guys were looking at powers of the letter I, the number I. And it has this cyclic nature as well, that when you do I to a power and then you do I to a one bigger power and one bigger power, you keep getting the same digits over and over again. This happens, right? You get sine, you get cosine, you get sine, you get cosine. The only thing that might change is the sign, positive or negative, on the front of it. That's it. There's one other that I'd like to mention, and it kind of fits in over here. So I'm going to kind of put this in over here as an asterisk. You can just write it out to the side. And it's what happens when you have the equation of a line. And so I'll use our standard mx plus b equation of a line. Technically, this fits in a couple of places, which is why your book doesn't isolate it on its own. It fits in this sum difference one, right, number 4. It's a sum. And it actually fits into the power rule because you have x to the power 1. And it actually kind of fits in with the constant multiplier rule as well because there's an m in front of it. So it's kind of a combination of a bunch of things, but the reality is that lines are very nice. Much like the horizontal line that we drew for the very first rule. The horizontal line, you knew what its slope was. Its slope was 0, right? You know what the slope of this is too. What's the slope of this? It's m. So if we're dealing with something that's linear and we're looking for its slope, it's just m. Right? That's what the slope is. And if you think about it, that's actually, using all these rules, if you want to think about it separately, what's the slope of what's the derivative of the b? Well, it's 0. That's the first rule. What happens to the m? It comes along just like it did. What happens to the x? Well, let me actually show you because it's kind of interesting. This x is x to the 1, right? And if you were to take its derivative, you'd bring the 1 down and you do 1 minus 1. What's the value of 1 minus 1? 0. And what's x to the 0? 1. So again, you actually get that piece being 1. So this piece stays, this piece becomes 1, and this piece becomes 0, leaving you, in fact, with m. So it is a combination of the other rules, but it's also easier just to look and say, hey, it's a line. Its slope is m. Okay? So what we're going to do, basically, in the rest of the lesson, is utilize these rules, to find derivatives instead of using limits. So I know sometimes students are like, well, if you've got simple rules, why do I have to do the limits? Well, here's the deal. All these simple rules came about because somebody did the limits definition enough to realize there's a pattern, right? That's where they come from. All of these rules come from the fact that there's the limits created a pattern when it was done enough times. So that's why we start with that. So taking a look at number 1, x to the 7th, what is the derivative of x to the 7th? 7x to the 6th. And it's important to notice that we are finding y prime. So make sure and designate it as such. Whatever the derivative notation is, we want to make sure it says that, not the original function. Okay, is everybody good? 7x to the 6th. That's a basic power rule. The next one, notationally, I have f prime of t like so. Be aware in WebAssign, your WebAssign, if you haven't noticed it already, is very, very particular that you use whatever the variable is supposed to be on that problem. So if you switch something into x and there's a variable t, it's going to tell you got it wrong. So be careful of the variable use in that way. So taking a look at this one, the first thing that we might notice is that there's a pi, but pi is a constant. It's a number, right? So the constant multiplier rule says that it just comes along for the ride. And what's the derivative of cosine? Negative sign. Now, I could write the pi there and then in parentheses next to it write negative cosine, but it would just be easier to put the negative in front here. Agreed? Yeah, so we'll just move it to the front. So the negative comes from the cosine becoming negative sign. Some functions, much like the two we just did, very much just look like one of the rules and we can just start. But sometimes they don't. They look a little different. Now, I didn't tell you anything about what happens when you have a denominator, all right? So when you have a denominator, it's a variety of things that can happen. It kind of just depends on what the denominator is. In this particular one, we have a single term in the denominator, right? There's things multiplied, but it's a single term. There's no addition or subtraction. And because of that, we have the ability to change it so that it looks like one of the other functions that we've seen. In particular, the numbers don't move. So as I rewrite, my 4 and my 3 stay put. They're not moving. But there's a property of exponents that says that if I have x squared in the denominator, I can write it in the numerator in a different way. How can I write it?
X to the negative.
Yeah, x to the negative 2. So you can write it out to the side if you'd like, or you can actually put it in the numerator with the 4 if you'd like. It doesn't matter. But it's x to the negative 2 instead. And that actually becomes something that we can work with the rules that we have already. So the constant multiplier says that we leave the 4/3. This is y prime. And then the x to the negative 2 we have to deal with. So what is the derivative of x to the negative 2?
Negative 2x to the negative 3.
Yeah, negative 2, and then it's x to the negative 3. Right, we decrease negative 2 minus 1 is negative 3. Now, let me make a comment here because it's valuable to note. When you get to your derivative gateway that we're going to be doing next Friday, this isn't the quiz this coming Friday, but next Friday, when we get to that and you're doing a whole bunch of derivatives for me, I'm perfectly fine with you leaving it just like that. You aren't expected to simplify a single thing, okay? Now, for WebAssign and for your quizzes and your tests otherwise, I would expect some basic simplification to happen, right? The reason it's not happening on the gateway is because that's not what the gateway is testing. The gateway is testing your application of the process, of the rules, not testing your ability to simplify there, okay? So we are going to simplify that. In particular, a couple of things. No negative exponents, right? However the problem started, it should end. This problem had no negative exponents to begin with, so it will have no negative exponents in the ending of it. And then anything that I can multiply or divide to simplify, I will. So I can put that x cubed back in the denominator. This negative 2 is like negative 2 over 1, so I have negative 8 on top, and I have 3 on bottom. Does that make sense? Just cleaning things up a little bit.
So when you put the exponent on the bottom, you just take off the negative?
Yeah, so there's a property, I'll write it here because I have a little bit of space anyway, that says that when you have a negative exponent like this, that you can change its location and make it positive. And it's true the other direction too. Like if you had 1 over x to the negative n, you can bring it up and make it x to the positive n. Yeah. We'll encounter one more, but I don't think it's today, where we're changing a little bit of notation. No, it is today. It's actually number 5 coming up. Let's do 4 first, though. Okay, so again, we have a fraction. And while the denominator is a single term, bringing it up to the numerator would then create a product. Agreed? And right now, I haven't told you what we do when we have products or quotients. We have rules for them, but we haven't discussed them. And the reason we haven't is because on this kind of particular problem, we don't need it. And here's why. This has a way to simplify using fractions. Okay, so remembering what you know about fractions, does that make sense so far? We usually use our properties of fractions the other direction. We usually take things that are broken apart and we mush them into a single fraction. In this case, I'm trying to separate it out into each individual fractions. But the direction doesn't matter, we can do both. So we'll simplify what's there. So what is x cubed over x squared? X. What is negative 3x squared over x squared? Negative 3. And what is 4 over x squared, at least rewritten helpfully? Right, like the last problem, yeah? Okay, 4x to the negative 2. Is that good so far? So right now I haven't done any calculus. That is all algebra. Okay, so now we're ready to do calculus. What was my function name? G of x. So we're going to do g prime of x. What's the derivative of x?
1.
It's 1. So there's an understood coefficient in front here, 1. Right? And the derivative, 1x is a line. So the derivative of a line is its slope, 1. So it is 1. What's the derivative of the negative 3? 0. So I'll put negative 0. I'll just put 0 in here just for a placeholder for the moment so that if you're looking back, you realize that we didn't just make it disappear. It really is 0. How about the 4x to the negative 2?
Negative 8x to the negative 3.
Okay, everybody good so far? All right, bare minimum of what we have to do is we have to rewrite it so there's no negative exponents because the original problem did not have any either. So there's a 1 at the beginning. I don't need to write the minus 0 again. And then I have negative 8 over x squared. Cubed, sorry. Cubed. Depending on if you were checking the back of the book or if WebAssign freaks out and tells you this is not correct, it might want you to create a single fraction. Again, I don't think WebAssign is going to do that to you, but if you were looking at like one of the quiz questions, it might merge it back into a single question, a single fraction if you were looking at a back of the book problem, okay? There's nothing necessary about that. It's just an alternate way of expressing it. So at this point, we would be finished. But again, I'd kind of like to make comment that if you were doing the gateway for me next Friday, week and a half away, you could actually stop a step before, and it would be fine. Okay? All right, number 5 has radicals, and I have not either talked about what to do about radicals, much like we didn't talk what to do about denominators. Well, radicals have what are called rational exponents. So this is another algebra topic that you might remember. It says that if you have the nth root of x to the m, that you can rewrite that as x to the m over n. That's the property of rational exponents. And so what that means for us on this one is that this is, right, an understood 1 power inside of the cube root. So I can rewrite this as x to the 1/3 and x to the 1/5. Yep. So again, that's just rewriting with college algebra, algebra 2 from high school. Okay. So now we're ready to take derivatives, though we haven't actually done exponents that are fractions. We can. Our power rule applies just fine. You just have to think a little bit more carefully about your subtraction. So the 1/3 will come down. This is x to the 1/3 minus 1. I'll write it this time only. Next time I'll just move forward. Okay? We're going to clean that up in a minute in a couple of different ways. And then I have my 1/5 x to the 1/5 minus 1. And as maybe awkward and silly as it seems to you that I wrote the 1/3 minus 1 and the 1/5 minus 1, if you did this on the gateway, I would accept it. And it would be okay. So what should those numbers actually be? So let's do that real quick. What is 1/3 minus 1? Negative 2/3. And what is 1/5 minus 1? Yep, negative 4/5. Okay, is everybody good so far? Because I'm definitely not finished in terms of I can't leave my answer that way for WebAssign or for a quiz or a test or something. Gateway's different, right? So a couple of things. Number one, no negative exponents, and I definitely have negative exponents. Number two, it started out with radicals, right? Which means my answer needs to have radicals. So I need to put it back into radical form. So I'm going to deal with the negative exponents first because we've already talked about how to deal with them on the previous work that we've done. So we're simply going to put them into the denominator. So I have 1/3x to the 2/3 plus 1/5x to the 4/5. Now, if a problem starts out in rational number exponents like that, then you could just leave it that way and you'd be done, and that'd be okay. And there's chances that you could have problems that look like that, where the problem actually starts out looking like this instead, right? You start there, and then you would be done right now. But we didn't. We started with radicals. So we're going to use that radical notation with the rational exponents in reverse. So now we're going to take what we have, and we're going to write this as the cube root of x squared. Right? That 3 down here is the index of my radical, and the 2 stays attached to the x. And we'll do the same thing with the other piece. We have 1/5. I have the 5th root of x to the 4th. And I've mentioned this before. I can't remember if it was in this class now. Some of my content is overlapping between classes at the moment, talking about radicals. But there's no need to sort of think about like, oh, I need to rationalize the denominator. That's not a thing because this denominator's radical has an x in it. It's a variable quantity. So sometimes this variable is already in rational form in the denominator, and sometimes it's not. So there's no need to worry about rationalizing anything here. This would be our final version of that particular problem. Okay, any questions so far? It's probably worth saying that I don't really need you to write out the step where it says that you're subtracting 1/3 minus 1 and 1/5 minus 1. That's not necessary in most cases, but if it helps you, then by all means write that step. Okay, let's take this a little bit further. Our directions are actually going to have us find a line on this one. So it says to find the slope of the graph. Okay, slope of the graph is the same thing as derivative. So we're going to find the derivative at the given point. Okay, so the given point, we did this last class period, means that we're going to actually plug 2 in and find out what the value is at specifically x equal to 2. And then we're going to use the derivative and a graphing utility to confirm our results. So I'll show you how we do that when we get to that part of the problem. So the first part of the problem is just one step beyond what we've been doing today so far. So we're going to take the derivative of 3x cubed. That's so much easier than the ones we just did. What's the derivative of 3x cubed? 9x to the second. And then the negative 10 is 0, right? So now we're going to evaluate this, and I'm going to actually write next to it what I'm evaluating it at. It's at x equal to 2, so kind of like a function notation. I'm going to put a 2 in for x. I'm not multiplying y prime by 2. I'm just evaluating it. As you remember, exponents before multiplication, so we will do the 2 squared first, which will give me 4 times my 9 is 36. Okay, so this is the equation, or this is the slope, or excuse me, at x equal to 2. It says to use the derivative feature to confirm your results. I was stepping ahead of myself on the point, so we're going to find slopes. We're going to find some lines in a minute. I'm going to show you a cool feature in a calculator. You ready? Okay. I wish I could get this thing to actually show up on my screen. It's still not cooperating with me, but we'll work with it. So I would like you to write the original equation into y1. Okay, that's the 3x cubed minus 10 and y1. And I will need to borrow somebody's calculator who has a different operating system, because there's 2 ways that this will show up notationally on your calculator. Next. So it looks something like that. Some of your calculators are fancier. Mine's super old. And it actually puts the 3 up here. Some of yours do. It doesn't matter. Okay? So I want you to exit the screen. You're going back to the screen where you can add numbers together at random, right? Just a second quit. You're exiting to the regular screen. And the feature that I want you to select is to hit Math. And it's number 8. Just hit Math 8. Now, some of you, when you did that, you had something that comes up and says in deriv and a parenthesis. That's what mine says. If you did not have yours come up like that, let me know. Okay, I'm going to borrow Shelby's. Let's remember how she does that. Okay, let me write this down on the screen. So there's 2 different operating systems on these calculators these days. And it puts this little box right here. I'll do it in blue, like that. And then it has parenthesis. Whoops, that's not right. Parenthesis. There's another box here. End parenthesis. There's a vertical bar. And then there's actually a box here. And there's a black box in front of it, like a solid filled-in box. The blue boxes are what we're going to fill in on this notation in a moment. Huh?
Is that a black box or an X?
On Shelby's it's a black box.
Mine's an X.
Mine's a black box.
Okay, it shouldn't make any difference. If it's black box or an X, it shouldn't matter.
Mine's not an X anymore. Mine's not. Okay, I don't understand this. Mine's
Okay,
a box now.
just chill. It's okay. It doesn't matter which one it is. Okay, the blue boxes are what we care about. Okay, the blue boxes should look like dotted boxes on anybody who has that particular operating system. Is that true? Do the dotted boxes match my blue boxes? Cool. That's all I care about at this moment. Those of you whose calculators did what mine did, I'm going to talk to you first. What you're going to do is, this is the notation, and I'll show you where to find the pieces. Your notation is y1, comma x, comma x. That's the notation you're going to put in there. Now, you'll notice on the screen itself, you know where the x button is. And hopefully you see where the comma button is. Those are just actual buttons on this calculator. y1 can be found underneath the button that says vars. So if you hit the vars button, and this is true for anybody, actually, those of you who have the other notation are going to need this in a minute anyway. So click vars just so you can see where it is. And if you go under to the right-hand side to y vars, and then you go to the number 1 option, which is function, because we're working with functions, and press enter, you select y1. There's y1. Okay, is anybody not able to find y1?
Does that say Y1XX?
Yeah, it does. Yeah. Does everybody see where you find y1? Okay, so those of you with me who have the inderiv notation, you're going to select y1. Okay, so you're going to have your inderivs already there, and then you're going to tell it y1 by hitting vars, y vars function, and then pressing enter on y1. Then you're going to put a comma x, and I didn't mean an x here. This is whatever your number is. We'll get to the other notation in a moment, but it's the 2 here. So ours is a 2. 2.
So we actually enter an X there?
Yeah, on the second one. So you do y1, comma x, comma 2, close your parenthesis, press enter. And did it give you 36? With some level of mistake. Mine says 36 point a bunch of zeros and a 3.
Yeah, that's right.
It's 36. Your calculator is not using calculus. Isn't that amazing? It's using numerical methods to actually do an approximation. It does not do calculus. You are smarter than your calculator, believe it or not. Isn't that cool? You can tell that to your people at lunch today. My calculus teacher said I'm smarter than my calculator. You are. It can't do calculus. All right, those of you who have my notation with all the boxes, okay? Here's what goes in these boxes. I'll write it in red. This goes X. You know where the X button is. The big box in the middle is Y1. You'll pull it up the same way that we did on the other operating system. Vars, Y vars, function Y1. And then over here, the last blue box, you will write in it the number 2. So you have the same pieces that we had, right? X, Y1, and 2, just like we have Y1, X, and 2. It's just in different locations. And if you press enter, what does it give you?
0, 0, 0, 0, 0.
Yes, the same as mine did, right? The same error is happening, which is fine. It's 36. So you're using your calculator to confirm that your calculus that you did, which was actually quite a bit quicker, is correct. But you can verify. We're going to try another one. This one's got a little bit of trig in it. So we have f of theta equals 4 sine theta minus theta. We're at the point 0, 0. So first of all, we're going to find our derivative. Our variable is theta. So what's the derivative of 4 sine theta?
4 cosine theta?
Good. 4 cosine of theta. And what's the derivative of theta?
1.
1. Okay, so theta is like x. It's just a variable, right? It's a linear piece, actually, and its slope is 1. So anytime you have a constant or a variable x, y, z, whatever the letter is by itself, its derivative is 1. And we're going to evaluate then this at the value of x equals 0 from here. So 4 cosine of 0 and then minus 1. So do you remember what the cosine of 0 is?
1.
It is 1. So this becomes 4 times 1, or simply 4, minus the 1 at the end. My slope is 3. And let's use our calculator to verify real quick. So hit Math 8 and put those pieces in the way we did on the last problem. Except that your last number is a 0 because your x value you're inputting is 0. Oh, no, that's right. Oh, I never changed my equation. Make sure you change your equation. So sorry, I didn't change mine. The original equation has to go in y1. This one right here. Yours will show up as x's. It'll say 4 sine x minus x in your screen. That's fine. So over in y1, yours will actually say 4 sine x minus x in y1. And then you'll have the end deriv notation. Or something like that. Does it give you 3? Close enough. Yeah. Yeah, 2 point, a whole bunch of 9s and some 3s at the end. That's what mine says. Yeah. Yeah, it's 3, right? We're sufficiently okay with the fact that the calculator has got an error. That's okay. It's pretty close to 3, right? So yeah, it is the number 3. All right, let's flip over the page, take a look real quick at the last 2 pieces. This actually was what I was thinking we were at before. We're going to find our derivatives, but we're going to actually find tangent lines here. We did this on one problem last time at the very end of class, but it works a lot quicker here because we're not using limit definitions, we're using simple rules. So we start by doing the same thing we've been doing on the previous problems. We're finding the derivative. So what's the derivative of x to the fourth?
4x to the third.
What's the derivative of 3x squared?
6x.
And the derivative of 2? 0. Okay, everybody good on the derivative on that one? So we're trying to find the actual slope, which means plugging in the number 2. So we're going to find y1 of 2. So I have 4 times 2 cubed minus 6 times, I said 2 cubed and then I wrote 3. I don't know why. I wrote 2. 4 times 2 cubed minus 6 times 2. And what does that give me?
20.
It is, it's 20. And this 20, this derivative is a slope. It is the slope of a tangent line. Okay? We now have a slope, and we have an ordered pair. And from back in the day, and from last class period as well, I wrote this on the screen. This is one of my versions of this is my point slope form of the line. I can take y minus the y value, which was 6, equals the slope I just found, which is 20, times x minus the x value, which was 2. And I should be able to solve this equation. Simplify it, that is to say. So I have y minus 6 equals 20x minus 40. We'll add our 6. My equation is y equals 20x minus 34. And this is my equation. Is everybody okay with that point? I'll show you how to do it on your calculator real quick because I just mentioned it last time. What it's talking about on part B, using the graphing utility to verify, means taking your original equation and your slope of your tangent line equation and putting them both into y1 and y2. So we'll have x to the fourth minus 3x squared plus 2 and 20x minus 34. Probably worth saying that the 20x minus 34 is probably not a standard window kind of thing. Negative 34 means it's crossing way down at negative 34, right, screen-wise? And its slope is extremely straight. I mean, 20 is a very large slope for a calculator to deal with. So if you just hit zoom 6, your picture is probably not going to look very good right now. Looks like you have a W, and then you have this like line shooting up. That's okay. It's not too bad. If you wanted to zoom and shift around to see it a little bit better, you could certainly do that. But what you're seeing happening here is this point, what was it, 2, 6, roughly we'll say right there. And the line that it's drawing through that is extremely sharp, right? Very, very steep. You have this kind of an image. So feel free to play with your screen and your calculator if you don't like that view of it. But it looks pretty convincing because it is very steep on that W part over on that far right-hand side. All right, one last one, same directions, well, similar anyway. Actually, that's not similar at all. I totally just lied. I should probably just read things before I start talking. Determine the points, if any, where the graph has a horizontal tangent line. So to start with, it's talking about tangent lines, so we're talking about derivatives. So we're going to take a derivative. I absolutely do not like the letter S, so be really careful when you write your S's that they don't look like 5s. So S prime of x, we have 2x cubed over 3. What is that's derivative?
Two.
Okay, all right, so let's just, the 2/3 stays. Let's just deal with the x cubed. What's the derivative of x cubed? 3x squared. Okay, so the 1/3 and the 3 part that we're kind of coming up with, that actually ends up canceling when we do this part of the derivative. So we'll clean that up in a second. We'll take one more step. What's the derivative of x squared over 2? We'll do the same thing. I'm going to leave the over 2 part. What's the derivative of x squared? 2x. Yeah. What's the derivative of negative 3x? Negative 3. Remember, linear ones just take the constant in front, the coefficient. And what is the derivative of 27? 0. So as we clean this one up, my 3's canceled, so did my 2's. This actually ends up being a lovely one. It's actually 2x squared minus x minus 3. That's lovely. There's my function. Horizontal tangent lines. So horizontal lines, what can you tell me about horizontal lines?
Zero.
Okay, zero slope, their y values are the same everywhere, right? Yeah. So there, in particular, because we're talking about slope, the fact that it's a zero slope is the important part for us right now. This has a zero slope. And so the question is actually asking me, horizontal tangent lines, it's asking me where is the derivative 0. So I take the equation that I just got, 2x squared minus x minus 3, and I set it equal to 0. And all of a sudden it feels like you're back in algebra and you're looking to either use factoring, quadratic formula, completing the square, something like that, as you're working with the problems. So this one does factor. That's usually our go-to to try first. So I need 2x and x. My signs need to be different in order to get a negative 3 at the end. So let's go with positive and negative. And then I need to put my 3 and a 1 because that's what I get to multiply to give me the 3 at the end. So you can try some things, right? If you try the 3 and the 1 here, you find out that this is positive 3 and negative 2. So, so it's the right value, but it's the wrong sign, right? Is that true?
Mm-hmm.
Yeah. So if it's the right value but the wrong sign, all it means is that I put the signs in the wrong place. If it's actually not even the right value, then I need to switch some numbers around as well. So this should have been a negative and this one should have been positive. We set each one of these equal to 0. And we get x equals 3 halves and x equals negative 1. Is that good so far? Okay, there's one last thing to do. It actually asked us to determine the points. And right now I found the x values. So I have two x values. I have x equals 3 halves. And I have x equals negative 1. And if I didn't know what, that was accidental. 3 halves and negative 1. I'm not going to belabor the point, but you could actually put it back into your equation, right, the exact equation that you were given. If you do it in fractional form, it's 189 over 8. If you're not sure how to make your calculator give you fractions, I can show you that. And this is 173 over 6. If WebAssign allows you to use decimals for it, you can use the decimals for it as well. The corresponding decimals here would be 1/2, 1 1/2, excuse me. And then it's 23.625. That one's actually terminating. The other one is negative 1 and 28.83, and the 3 repeats. So depending on what the version asks you to do. Okay? We're done. 2.2 is finished, so 2.1 and 2.2 for homework. Success Center is open as normal, as are my office hours. And we will have a quiz on Friday.